Hello students, so in this video we're going to look at some examples from the homework in section 4.2 on the binomial distribution. The book gives the definition of a binomial distribution and the four conditions that a binomial distribution must satisfy. So before we jump into the examples, let's go over the definition and the four conditions. Okay, so there are many probability experiments for which the results of each trial can be reduced to two outcomes, success and failure. So for instance, when a basketball player attempts a free throw, he or she either makes the basket or does not. So probability experiments such as these are called binomial experiments. So in other words, a probability experiment is a binomial experiment when you can classify the outcomes as either a success or failure. Okay, but there are other conditions that need to be met. So let's discuss those conditions. Okay, so a probability experiment is a binomial experiment when there are a fixed number of independent trials. Okay, so the letter N will represent the number of trials. And what we mean by independent is that the outcome of one trial does not affect the outcome of another trial. Alright, each trial only has two outcomes, right? Success and failure. So success is the thing that we are interested in studying. Okay, it doesn't necessarily mean it's something good. Alright, condition 3 says the probability of success is the same for each trial. So the lowercase letter p will represent the probability of success, and then q, the letter q, is equal to 1 minus p, that's the probability of failure. And then lastly, the random variable x counts the number of successes in the n trials. Okay, so x would be a whole number between 0 and n. Okay, so to answer the first question on the homework, it says that in a binomial experiment, what does it mean to say that each trial is independent of the other trials? So based on just what we just covered, right, you would select the appropriate answer choice. Okay, so the next example asks you to determine if the experiment described in the problem is a binomial experiment. Okay, so what you're going to do is you're gonna read the description. All right, and then determine, right, whether that experiment satisfies the four conditions for a binomial experiment. Okay, so remember the conditions are that you have a fixed number of trials. Okay, and the trials are independent of one another. Okay, and that there are only two possible outcomes, success and failure. Okay, the probability of success should be the same from trial to trial. Okay, and the random variable counts the number of successes in n trials. Okay, so you would select yes if the experiment is a binomial experiment, and then answer the questions that follow, right? Or you would select no. So I'm going to go ahead and skip number 2. Okay, and I'm going to go to number 4. Or rather, question number 3, which says that a state lottery randomly chooses 5 balls numbered from 1 through 44 without replacements. And the key there is without replacement. And it says you choose 5 numbers and you purchase a lottery ticket. Okay, so the random variable represents the number of matches on your ticket to the numbers drawn in the lottery. And it says determine whether this experiment is binomial, and if so, identify a success. Specify the values of n, p, and q, and then list the possible values of the random variable x. So before we answer this question, let's see if we can find a similar example in the book. So we have example 1 on page 202, which asks you to identify whether an experiment is a binomial experiment, and they give you 2 examples. Okay. So the directions say to determine whether each experiment is a binomial experiment, and if it is, specify the values of n, p, and q. Okay, N is the number of trials, P is the probability of success, Q is the probability of failure. And then it says to list the possible values of the random variable x. Okay, so remember the random variable x should be counting the number of successes. Okay, so and if it's not a binomial experiment, you have to explain why. Okay, so if you read the description for number 1, right, you'll see that it is, right, and you can look at the solution to see why it is a binomial experiment. So let's go and look at number 2 here. Okay, so number 2 says a jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacement. So the keyword there is without replacement. So it's just like the problem we are working on. All right, and then it says the random variable represents the number of red marbles. Okay, so we have this jar with the different colored marbles, red, blue, and green. So even though there are 3 different colors, right, the marbles we are interested in are the red marbles. So when we selected red marble, that's considered a success. If we select some other marble, right, that's considered a failure. Okay, so remember the problem said that we're selecting these marbles without replacement. So that means when we select the marble, right, we take it out and don't put it back in the jar. So that's really key for helping us understand how to answer the question. Okay, so there are a total of 20 marbles in the jar to begin with. So you have 5 red, 9 blue, and 6 green for a total of 20. Okay, so total of 20 marbles. Okay, and then 5 of them are red. Okay, so when you select the marble on the first trial, okay, the probability of a red marble, so I'm going to abbreviate, so P of R means probability of red. So when you select the first marble, the probability of a red marble is 5 out of 20, right, because there are 5 red marbles out of a total of 20, so 5 out of 20 would be 1/4. Okay, you can simplify that as 1/4. Okay, but remember, right, when we select that marble, right, we don't replace it, right, so we take it out, right, so that means we have 1 fewer red marbles to select from, okay, and then 1 fewer marbles in total, right, so now we have 4 red marbles, okay, and now the total number of marbles in the jar is 19, right, so what would be the probability of success on the next trial, right, when we go take out another marble, what's the probability of selecting another red marble on the second one? Right, you'll see that it's different, right? The probability changes now, right? Okay, so now we have 4 red marbles to select from. Okay, and 19 total, right? Because we took that marble out. Okay, so 4 out of 19 we can clearly see is not equal to, right, our probability of 1/4. Okay, so in other words, the probability of success changes from trial to trial, right? Then we can do this again, right? So again, if our first 2 marbles are red, okay, right, now we have 3 red marbles and then a total of 18 marbles to select from. Okay, so the probability of selecting a red marble on your third pick is also different. Okay, right, it's not equal to what it was originally, right? It's not 5 out of 20, right? It's 1/4. Okay. So now it's 3 out of 18, okay, which you can simplify, right, as 1/6. Okay, so clearly the probability of success is changing from trial to trial, right? And remember, right, one of the conditions was that the probability of success must stay the same. Okay, so because we're selecting these marbles without replacement, that means that the probability of success will change from trial to trial. So to answer the question, the answer is no. Right, because the probability of success is different. Okay, so read the answer choices carefully and then select the best answer choice. Okay, so even if the other conditions are met, right, it still doesn't make a binomial, right, if the probability of success is not the same. Okay. It says identify a success. Well, clearly a success is selecting a red marble, but remember, this is not even a binomial experiment to begin with, so we're just going to select answer choice B. Okay, but if this was a binomial probability experiment, right, then the success would be is matching is a number that matches the numbers on that are drawn from the lottery. But this is not even a binomial experiment. Okay. So don't confuse the example I went over the book with the example that we're now working on. Okay. So the reason that this is not a binomial experiment is because, right, when you select your numbers 1 through 44, right, you cannot select a number twice, right? So once you select a number, you cross it off, select your next number. Okay. So the probability of matching a number, right, changes as you select a number. Okay. Lastly, so specify the values of n, p, and q. Right, so clearly this is not a binomial experiment. Okay, so we're going to select answer choice B. Okay, but if this was a binomial experiment, you would enter the number of trials. In this case, if this were a binomial experiment, right, you would enter 5, and then p would be the probability of success, and q would be the probability of failure. Okay, and it says list the possible values of the random variable x. Again, this is not a binomial experiment, so you would select answer choice C. Okay, so that's how you complete this question, right? When the experiment is not a binomial experiment. If the problem had said instead, right, with replacement, right, then it would change. Then the probability of success, right, the probability of the number of matches, right, would be the same. But because it's without replacement, the probability of matching the numbers that are selected is not the same. Okay, so let's look at the next question here. Okay, so in question 4, you're actually going to calculate binomial probability. So in question 4, it says 58% of U.S. adults have very little confidence in newspapers. And it says you randomly select 10 adults. And it says find the probability that the number of adults who have very, very, very little confidence in newspapers is A, exactly 5, B, at least 6, and C, less than 4. Okay, so let's see what it says in the book here about calculating binomial probabilities. Okay, so there's something called the binomial probability formula, okay, which we're not going to use, right? So if you don't have a calculator that can do this, right, you would use this binomial probability formula to calculate probabilities from a binomial experiment. Okay, so what we're going to do instead is use StatCrunch. Okay. So there's a binomial probability calculator that we can use in StatCrunch. So let's go to the Stat menu, go to Calculators, and then select Binomial. Okay, and what you're going to enter is the number of trials, and then the probability of success. Okay, so in the problem, okay, it says we randomly select 10 adults. Okay. So those are the number of independent trials, so n is equal to 10. Okay, and then the probability of success is 58%. Okay, so you want to convert that 58% to a decimal. So 58% is a decimal. It is 0.58, so you take the decimal point and the percentage, move it 2 places to the left. So our probability of success is 0.58. And that's what we're going to put here in the calculator. Okay, and part A says, right, find the probability that exactly 5 have little confidence in newspapers. Right, so exactly means equal to. Okay, 5 is already selected conveniently. Okay, so the 3 decimal places, the probability is 0.216. Okay, so on part B, we want to find the probability that at least 6 adults have little confidence in newspapers. So we're going to select greater than or equal to. At least means greater than or equal to. Change that to a 6. Click compute. So the 3 decimal places, the probability is 0.582. Okay, and then answer that last one, you would select less than, and then type in the number